Elastic potential.
Elastic potential energy. And what is it?
It's going to be the integral of the.
It's equal to the integral of
Tension between elements.
The dot product of F and the cross product.
It's just because it's not the x but x is real x, so it's the integral from u to 1 of half k ux.
I think we have to bring up the elastic by like every
Elements of
into
the-
differential.
Yeah.
Yeah, into like
So we have to calculate the elongation of
Yeah.
the element of the.
yeah. So that means it's like whatever the definition of like any particular contestant is.
Yeah.
well, let's take back a little bit. It's not as complicated as you think. So first of all, this string is already in tension, right?
Yeah.
Otherwise, it cannot support any weight until it has a nonlinear deformation. Okay, and second is, again, if we ignore nonlinearity here, we are considering very small deformation of the rope, right? So which means the deformation of the rope is not going to cause the tension to increase in a substantial way, right? If it does, then you get a nonlinear problem because the more weight you put in, the more tension you have. Okay, so if that assumption is made, which means the weight does not change the tension, then the amount of potential energy increase here is just the tension times what?
The change in the.
Yeah, the change in the length, right?
Oh, yeah.
Okay, so it's actually equal to the tension times the change in the length. Now what is the change in the length?
Oh, that was.
Yeah, that was the integral part, right? So of course the original length is 1, so I have minus 1 here. And then I have the integral from 0 to 1 of what? You know how to calculate the length of of a curve, right?
U squared x square root u squared x squared.
Can you say again?
The square root of
Yeah.
u squared plus x squared.
du squared plus dx squared.
Yeah. Thank you.
Yes. Okay. So du square plus dx square, right? So if I pull it out, it'll be tension times I have a dx square root of du over dx plus 1 squared, right?
Yeah.
Okay. And again, we are using we have a small deformation. So du over dx, if this is much smaller than 1. Yes, you have a question?
Just re-explain why we have minus 1.
How do I what?
Can you just re-explain why we have minus 1?
Oh, that's how much. I don't have to have the minus 1, right? So if I just so if I have the minus 1, it's the elastic potential change, right? And I actually don't have to have the minus 1. So let me actually get rid of it. I mean, at the end, the minimization statement is going to look like the same if I have a minus 1 or not. So let me just do the simple thing without a minus 1. So if du over dx, which is the slope, right, is much smaller than 1, which means the deformation is small. Can I do a little bit of simplification to this?
So Taylor expansion.
Yeah, standard Taylor expansion.
Is that ever not going to be?
So Taylor expansion is not just useful in numerical analysis, it's actually useful in dealing with a lot of physical problems, right?
1/2 du dx squared.
Yes, so the slope of a square root at 1, the first derivative is half, okay? Right? Because square root is actually the half power, right? So okay, so this is approximately equal to t times integral of 0 to 1. Now it's 1 plus, right? 1 is the value of this whole thing when du dx is equal to 0, plus the derivative, which is half, times du dx square, right? Dx. And now you kind of see why I was trying to put a -1 over here, because it cancels with that guy. So, but it doesn't matter. It's just a constant term. All right. So at the very end, my minimization problem is I'm going to minimize the integral from 0 to 1. First of all, I have the gravitational potential energy F times U, right? And then I have the elastic energy. Let me just ignore the plus T over here because it's a constant. If I include it in minimization or not, it doesn't make a difference. Half of T times du dx squared. This thing dx. So the physical problem is the ultimate deformation of this string is going to be a function u, such that this integral is minimized. Okay?